Hello everyone. In this video I'm going to be doing a few examples of solution stoichiometry. And so something that I've kind of discussed a few times in my previous videos, actually a lot of times in my previous videos, is if you have some way to convert your value, your unit that you're given into moles, do it. Because the great thing about moles is there are a lot of conversion to get you from moles into something else or to go from something into moles. And so stoichiometry, we've discussed this concept in the past, but the previous examples we have been talking about mass stoichiometry. And so in mass stoichiometry, we used molar mass to go from mass to moles to moles to mass. But in this case, we now know something about molarity, so now we can actually use the same exact relationship if we have a balanced chemical equation and some molarities that will relate from volume to moles. We can now go from volume to moles to moles to volume. Or if you want to get crazy with your math, which unfortunately you're probably going to have to do at some point in your future, we can also go from volume to moles to moles to mass. Or mass to moles to volume, or volume to moles to atoms, or atoms to moles. You know where I'm going here. And so, if you have a balanced chemical equation, you know the relationship between moles of one of your substance and moles of the other substance. If you have the molarity, we know how to go from volume to moles. If we have the molar mass, we know how to go from mass to moles. If we have Avogadro's number, which you always have handy, then we know how to also go from things to moles. And so in these situations, all you need to do is just line everything up appropriately. And so, warning, I already told you this is going to happen. This scheme is just going to keep growing bigger and bigger and bigger. And same kind of deal as what we saw in the last, or two videos ago, in which case you saw this half of it. But again, we have molar mass, mass to moles, molarity, volume to moles, Avogadro's number, things to moles, balanced chemical equation. You can tie all of this stuff for B to all of this stuff to A, and hell, you can go to C and D, but if you have a balanced chemical equation, you have a link between two different substances. And so, in these word problems, one thing I've seen a lot of students mess up on is they panic before they even finish reading the question. But if you can just take a deep breath, read the question calmly, you'll realize that I'm essentially giving you everything. You just need to arrange it appropriately to get rid of all the units you don't want at the end. So, example. If we have magnesium is the second most abundant metal in seawater after sodium. The first step in its industrial extraction involves reaction of magnesium 2 plus with their calcium hydroxide to produce magnesium hydroxide. So what mass of magnesium hydroxide is formed when 0.180 liters of 0.0155 molarity magnesium chloride reacts with excess calcium hydroxide? And so in this case, and I'll also give you the molar mass of the magnesium hydroxide. And so for this particular one, you have to, again, ask yourself the basic questions. What am I given, and what am I being told to solve for? And so in this situation, reading the last question even, or the last sentence, sorry, I am asking for the mass of magnesium hydroxide. But I am giving you information, volume, and molarity of magnesium chloride. So remember, the only way that you can relate two entirely different complexes is if you know a relationship between them, like a balanced chemical equation. But once you have a balanced chemical equation, you know the relationship between the moles. So now you need to figure out how to get the mass, from moles to mass and from volume to moles. But as we've kind of mentioned a couple times by now, we know how to do that. And so we know that if we are given volume and molarity, we can solve for moles. We also know if we're given, in this case I actually give it to you, if we're given the molar mass, we know how to go from mass to moles or mole to mass. So the only real thing you have to do is write a balanced equation and then take all the information I give you and line it up correctly. And so the balanced chemical equation for this one is MgCl2 aqueous plus calcium hydroxide aqueous gives you magnesium hydroxide solid plus MgCl2 aqueous. And so, please note, I didn't technically tell you this was a solid, but one hint that this may be the precipitant is I'm asking for the mass of it. typically in chemistry, we normally don't ask for mass of liquids unless we give you a density along with it. And so that could have been a hint. In addition to that, hydroxides are normally going to be insoluble, and magnesium 2 plus is not one of those exceptions. And so that's why we have our magnesium hydroxide is going to be a solid. Chlorides, on the other hand, mostly soluble, calcium, not one of the exceptions. And so when we kind of go through and look at this, we are going to have sorry about that, my computer had a little hiccup. So back to where I was saying. Magnesium chloride plus calcium hydroxide to produce magnesium hydroxide solid plus calcium chloride. And so we are asking about mass of magnesium hydroxide. We're given information about magnesium chloride. So the relationship between our magnesium chloride and our magnesium hydroxide just happens to be a 1-to-1 relationship. But this is moles. So now we need to figure out how to get this information into moles. And so luckily for us, we know that if we have the volume and molarity, mentally or physically scribble this M out and write moles per liter. And so we know how to go from volume into moles using molarity. We know how to go from moles of this to moles of that using our balance equation. And last but not least, we know how to go from moles of magnesium hydroxide back into mass, which my mass disappeared. It's on the previous slide, so rewind it if you want to see it. In this case, we know we can go from moles of magnesium hydroxide to mass using the molar mass. So write it all out. Make sure everything cancels the way you need it to. We have volume in liters. Put volume in liters on the bottom. We have moles of magnesium chloride into moles of magnesium hydroxide. Make sure moles cancel out. We're at moles of magnesium hydroxide. Using the molar mass, we can go from moles of magnesium hydroxide, put moles on the bottom and cancel out. We're left with grams of magnesium hydroxide. Please notice this is the same exact setup as mass spectrometry, except we're using a different unit, so we have to use a different conversion. But we're still going from thing to moles to other thing. And you still using the same balance equation, still using 1-to-1 because that's what it says in the balance equation it has to be. Let's do another one just to make sure you guys are on the right track. In a simulation mercury removal from industrial wastewater, 0.05 liters of 0.010 molarity mercury nitrate reacts with 0.20 liters of 0.10 molarity sodium sulfide. So how many grams of mercury sulfide, and I give you the molar mass form. And so I have this written in red letters, giant, actually they're all capital at the beginning and there's stars around it, so it has to be important. So if I give you information about more than one reactant, you have to remember a red flag should shoot off in your brain saying that has to be a limiting reactant problem, because there's information about more than one of these reactants. You don't actually know, well, you might if you're really good at math, but you don't know which one right off the bat is going to be the real situation. And so the same way that we did limiting reactants with our mass stoichiometry, same rules still apply. Now you need to take both of your reactants and convert the reactants in the product, figure out which one is going to be the limiting reactant, and then you can use that one as your mass. And so this next little picture that I have here, it looks intense, but I wrote it side by side. That's the only reason why it looks scary. And so same steps. We have volume of our mercury nitrate right there. We have our volume of our sodium sulfide right there. We have our molarity of both of them, so we know how to go from volume to moles. And we need to know how to take this volume into moles. And then once we're at moles of our reactants, take both of the reactants and convert them into the same product. And so in this situation, because I'm asking about mercury sulfide, it's probably the easier salt or product to form it into. And once you have moles of your product, convert it into mass by using the given molar mass. And so here, balanced chemical equation, step number 1. Mercury nitrate plus your sodium sulfide, aqueous, will give you mercury sulfide and our sodium nitrate. So remember, sulfides are normally insoluble. Mercury is not going to be one of those exceptions. And so in this case, you're going to have your solid. This one has to be an aqueous on a double whammy. Sodiums, nitrates, always, 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 always are going to be soluble. And so we kind of go through and take a look at this. There is a one-to-one relationship between each one of the reactants in the product. And so now we just need to make sure to convert our volume into moles. And please pay attention to my color coded here. And so I have 0.050 of my liters, and I have 0.01 moles per liter. And then we have a one-to-one relationship between our mercury sulfide and our mercury nitrate. And I give you the molar mass that tells you that there's 232.7 grams of mercury sulfide for every 1 mole of mercury sulfide. So here we just need to set up everything correctly and make sure all the units cancel out that we don't want. Similarly, do the exact same thing with the sodium sulfide. So we use our 0.20 liters and our 0.10 moles per liter to convert from volume of sodium sulfide into moles of sodium sulfide. Then one-to-one relationship between our mercury sulfide and our sodium sulfide. And then last but not least, convert our final moles of mercury sulfide into grams. And so looking at these two values, you should be able to tell me that 0.12, sorry, I forgot my grams in there, but my 0.12 grams of mercury sulfide is the maximum amount of product that's ever going to be produced from the combination of these two.